Good morning. Thank you for making it here at 9 o'clock on a Saturday morning and not the first Saturday morning. To help enthuse you for the day, we're going to start by talking about the core. The brief I was given was Seismology of the core, and the caption for this movie poster is, "The only way out is in." So let's see what we can find, where we can look, how we can relate this to what we've heard from mineral physics and geodynamics and geochemistry so far. One of the things we've already talked about a little is what the core is made of, and this is from a very famous paper by Birch, and you'll see another excerpt from that paper later. Essentially, this is Birch in the middle of his argument saying, iron seems like a good bet. He rules out other objects, and he's voting for a predominantly iron core, although alloying with lighter elements, conceivably including metallic hydrogen. Not quite sure about that one. Let's not push that one any further. But in 1952, Birch had some sort of idea about the mineral physics situation we're in. We've seen some beautiful pictures like this already. We've talked about Earth's dynamo. That was what we spent a lot of time hearing about yesterday. The behavior of Earth's dynamo actually may influence what we can see of the inner core. Some of the quirky properties of the inner core may be related to the magnetic field, and I hope to have time to come back to this paper later as well. And everybody likes meteorites. So these are a pair of iron meteorites. So when we think of the Earth as a differentiated body, we could be comparing Earth's core to guys like this. This is the Henbury meteorite. This is the Grosvenor meteorite. They're different parts of bodies which managed to differentiate and had something akin to Earth's core. You can play the same tricks and say, hey, maybe this is what the core of Mercury looks like, although maybe with some different lighter elements. You could do the same thing about the core of the moon for people who are thinking about lunar structure. How similar is Earth's core to the moon's core? And I'm afraid I don't know the answer to that question. But what I can tell you about is the core that we know we have in Earth today. So this is Richard Oldham. He has an impressive moustache. It's not as good as Maxwell's beard from yesterday's photo. And he was thinking about how you could look at the core. And this is what he said. Many theories of the Earth have been propounded at different times. The central substance of the Earth has been supposed to be fiery, fluid, solid, and gaseous in turn, till geologists have turned in despair from the subject and become inclined to confine their attention to the outermost crust of the Earth, leaving its centre as a playground for mathematicians. So I'm not quite sure it's a playground just for mathematicians, but I'm fairly sure it's a nice playground for siderites. So this is the paper where Richard Oldham said, there's a core down there. And there are some technical issues and some things probably we'd say are maybe just not right in his paper. But he noticed when he plotted distance from an earthquake to a seismometer and the time it took for the first and second phases of preliminary tremors, so we want them to be P waves and S waves, but some of them probably aren't. He noticed that as you go out in distance, there is an extended jump here. So you've got a discontinuity in the travel times. And so what Oldham pushed on and proposed was that the Earth looked like this. There was some sort of central body with a radius about 4/10 Earth's radius, where the properties were different. You have a distinct core. Can anybody see why I might be unhappy with this model of the core? I guess first of all I should read out the caption. The broken lines represent the first phase, the broken and dotted lines the second phase, and the continuous curve, well, that's actually the surface waves around the surface, so you don't see those. But why might I have problems with the first phase and second phase going through the core? Yeah, so I'm not personally thrilled about S waves going through the core, and you know, probably these things that he's recorded as S waves are actually SS waves. So you've got an earthquake, you've got an S wave which propagates through the mantle, bounces at the surface, and then does the same thing again. So you've got one S leg and two S legs. So probably these chaps up here are SS phases. Nonetheless, he's got the idea that something distinct and different is going on in the center of the Earth from really simple travel time observations. So this is 1906. Let's push this forward 7 years. We've still not quite reached the First World War, and at this point I'd like to say this paper is entirely in German, and Julianne and Renee sat with me and helped me try and work out what was going on, because this is a figure from a famous paper. This is a paper from Guttenberg in 1913, and he plotted this amazing velocity profile. So we've got shear wave velocity through the Earth and P wave velocity through the Earth, and again, you know, I'm going to pull a face here and say, well, he still has shear waves in the core, so he's not quite got it figured out. But he's got a core radius of 3,500 kilometers. It's virtually identical to Prem. And he's noticed some other things as well. Due to the velocity profile, he actually uses travel time curves, velocity plots like these ones to say some seismic phases we've seen that we didn't really understand are actually due to phases like SKS. So that's a shear wave which, when it gets to the core, converts into a compressional wave and then comes back out as a shear wave. So even though he was permitting still some sort of shear waves to travel through the core, he was saying that we're seeing things like SKS in 1913. So I guess we should have had a big party last year to celebrate this. I'm not quite sure. Push on a little further, though, and we have Harold Jeffries saying things like, there seems to be no reason to deny that Earth's metallic core is truly fluid. So we're going to ditch these shear waves propagating through the outer core, and we've got ourselves to a historical position where we have a liquid outer core. So there's a core down there. That should come as a shock to nobody. But the pictures are quite nice. As is this picture. This figure is taken from a paper by Bruce Bolt, which was taken from work by Inga Lehmann, in what I've always been told was the shortest ever paper title. She wrote her paper and she called it P prime. That's it. And then somebody told me last week there was a paper just called Q, and I guess maybe that wins, but I don't know if prime even counts as a letter. So P prime was a label that was given to a phase which traveled basically the whole width of the Earth, and you had different species of P prime, and I'm going to talk about body wave labeling in a bit. But what Lehmann had seen were waves which you would not expect to be arriving if you had a purely fluid core. So what she estimated, and I've drawn red circles on to highlight her lines, was that as well as having a core, there is some sort of distinct body inside the core. It's an inner core. And she drew straight lines on her plot. So all of these travel paths are just chords through the Earth, straight lines, so no velocity changes in the mantle. That's what your straight lines mean. And she got an inner core radius of 1,400 kilometers. We know that the inner core radius is about 1,220 kilometers, varies ever so slightly depending on reference model. So I'm kind of amazed by the numbers that people like Lehmann and Guttenberg managed to come up with. With these really, really simple methods, we can get really good observations of what's going on in the deep Earth. And we can then add more and more complexity, and we can find out all these strange and mysterious things the core does.
What is the P prime like? Which of those arrows are the P prime, or the reflection off the inner core?
So we've got a few different unexpected inner core arrivals. This one is this one is really dramatic. And there are some places where you actually get focusing of lots of different sorts of P waves. So I'm not 100% convinced that what she's seen. It's probably PKPDF, but it looks like it's at the caustic distance. So this number 5, where it's labeled as unexpected core arrival. Where is it on the seismograms? So we've got one arrival here and another arrival coming in here. It's not the most convincing seismogram I'm going to show you today.
Jessica, the inference that the outer core, the core was metallic, was that based on wave speeds? Or did the fact that the Earth generates a magnetic field play a role in helping people figure out what it might be? From reading these papers.
I think it's from a combination of things. I mean, and the discussion ebbs and flows in the literature. My understanding is that magnetism was a good pro for iron. But the consensus was reached slowly over the evolution of these papers, and I think Vern wants to say something about this.
Moment of inertia measurement, although I don't know the history of that.
Yeah, so I mean, and that would help you favor iron as well. But talking to people in the moon group, there are still suggestions that maybe the core of the moon isn't iron. Is that accurate, people in moon group? So I think we got a lot further, much more quickly on the Earth than we have on the moon. So we have models, and these are simple models of what the P-wave velocity looks like in the core. So from the CMB, we've got a really dramatic drop in velocity, and that's what focuses some of those waves and gives you the gaps in seismic travel times. For the P waves, we still have a P wave velocity through the outer core. You can see there are some differences in what's going on at the top of the outer core, some differences with what the different models predict at the bottom of the outer core, and slightly different velocity jumps at the inner core, outer core boundary. We've got PREM in red, AK135 in green, and IASP 91, which you can think of as a slightly older AK135 in blue. They agree pretty well. Probably interesting things are happening in both of these regions and in this region. One thing that seismologists should try and remember to tell people in other disciplines is that these models are built in different ways. So PREM is parameterized as a smooth polynomial in radius. So if you have exciting tiny flat features in PREM, you couldn't put them in because that wouldn't help you be parameterized as a smooth polynomial in radius. So if there was flattening of the gradient here, like you see in AK135 and IASP 91, PREM wouldn't necessarily represent that unless they'd chosen to put that structure in. And Ved wants to say something there.
No, I have a genuine question. There's no ulterior motive. How certain are we of the radius of the inner core boundary? So, for example, could we perturb it by 5 or 10 kilometers and yet still fit all the data? Do you know?
Well, it's either 3 or 4 kilometers different between these three models. So, does that help?
A little bit.
The models that we're using are not identical. Yeah. So if
It's like a P, which gives.
Yeah. So I mean, you can observe reflected phases off the interface, but each of these models will predict a travel time. The body wave travel times are best fit by AK135. This is something that we mentioned briefly last week. So AK135 probably has a good handle on it. But even in the models we're using, there are these differences of the order of a couple of kilometers out there. And that's before you do anything like put topography on the inner core boundary. And I know somebody had a poster on that last week. So I'm not going to pass any comment on the mineral physics at all. I'm just going to show you a pretty mineral physics plot to say that what we often try and do is take PREM, which is shown here by these black circles, and match them to whichever flavor of mineral physics you like best. And I've made this figure using this particular paper because it had a nice table in the paper. And I'm sure that many of the mineral physicists will prefer a slightly different mineral physics model. You can add a little bit of silicon, you can add a little bit of sulfur, you can subtract a little bit of oxygen, maybe a bit of carbons in there, maybe a bit of hydrogens in there. You can play these games and you can try and match density and VP. There are often problems trying to match shear wave velocity in the inner core with mineral physics models. There are different ways to solve that. You can ramp up the temperature of the inner core if you want. If you add the right combinations of light elements, you might be able to get things to work. One idea is you actually still have a little bit of liquid in the outer core, and that's why shear wave velocity, as found by mineral physics for pure iron, doesn't match particularly well with PREM. And I think that's an ongoing problem that seems like it's nearing resolution. And people play the same sorts of games for the outer core. Very brief detour into the outer core. This is a figure from a paper this year which played with the seismic velocities and adding and subtracting different elements from binary systems in liquids to try and match what seismology knows with what the mineral physics community has discovered about these properties. So we can take the velocities and the density profile, and we can do our best to match other disciplines. But what I want to spend the rest of today talking about is the seismic observations we can make. So this is back to our alphabet soup of seismic phases. And I'm not going to apologize for the fact that we have all of these different labels for all of these different core phases. What I'm going to try and do is be consistent in my usage of the labels. And if I say them very quickly, wave at me and tell me to explain again. When you have an earthquake, the first arrival at big distances will be the wave which goes through the fast inner core. And helpfully as seismologists, we give that phase two different labels. We'll either call it PKIKP, or we'll call it PKP-DF. The DF label is a historical one, but we'll use it anyway. And the reason we use it is one of the next phases to arrive is shown here in blue. That's PKP-BC. And again, the label is a historical one caused by the shape of the travel time curve. But essentially, PKP-BC travels through very similar paths in the upper mantle, slightly different paths in the lower mantle, but never quite manages to make it into the inner core. It stays in the outer core and then comes back out to the surface. There's a phase shown just below it here in purple. This is the phase which actually gets to the inner core boundary and then gets reflected off. And just as we had F and F in the mineral physics earlier this week, we have PKIKP and PK-ikp as our labels. So big I, you actually get into the inner core. Little I, you're just going to bounce off the inner core surface. Another phase that I'm going to briefly mention is this guy in green. This is PKP-AB. He makes it into the inner core, but doesn't manage to get very deep and then comes back out. So we've got these different core phases, and the reason that this is really useful is because we're trying to look at the core through a whole mantle. People who do mantle tomography make these beautiful detailed maps, and some days I just kind of prefer that the mantle was bland and completely homogeneous. So what we can do is we can look at pairs of phases, for example, PKP-DF and PKP-BC, look at their relative behavior, and we can say that that's probably not due to crustal structure because they go through the same bits of upper mantle and crust. It's probably not just because we've got our earthquake slightly mislocated. So we can probably use those phases to tell us something about the core.
I have a question. So what's the difference of the arrival times of the three phases?
Plot's about to appear on the screen. So a travel time curve maybe would help. So the difference between the travel times of these different phases is very small. And when I say very small, there's maybe, at the distances I personally look at, you'll get 5, 8, 10 seconds between your inner core phase and your reference phase. People who look at PK-ikp, PKP, at these short distances here, and this is something that Vernon's done, this is something that Lauren's done, we'll be looking at of the order of a couple of seconds between the different waves arriving. Which leads me on to a useful point to make here, that we do this at high frequency. So I will look at 1 second data, 1 hertz data. Because if you want to resolve something where your two arrivals are 3 seconds apart, you don't really want to be looking at long period data that's been filtered at 20 seconds. That's not really going to help you out very much. So we do this at much higher frequency than you'd look at global mantle seismology. This is high frequency seismology, and that's one of the reasons it's okay for me to draw lines as my ray paths. These waves do take up some volume as they travel through the Earth, but because we look at such high frequency, you can use a ray approximation and it's not tremendously wrong, as it would be if you looked at S waves in the mantle at 20 seconds. So here we're doing ray theory for the most part. We're going to be doing high frequency seismology.
What exactly does high frequency mean for this?
Oh, so anybody will tell you a different number for high frequency. When I say this is high frequency body wave seismology, I mean 1 hertz. I mean that ray theory is okay. If you talk to an exploration seismologist, 1 hertz is really, really low frequency. So if you're looking in a small patch of the Earth, then what you think of as high frequency will be different to what you think of if you're looking at the whole Earth. So this is high frequency for me for a global study at 1 hertz. Does that make sense?
City. So high frequency are going to attenuate after some distance, right? And you are looking out from the other side of the planet. So how big of an earthquake do you need to actually be able to resolve those various phases?
You stand a decent chance at a 5.5, but it's not really such a simple question as you want a number, you want me to say 5.5 or 5 or whatever. You can sometimes see core phases with a high magnitude 4, so 4.8, 4.9, but it completely depends on the mechanism of the earthquake. So is it pouring all of its P wave energy down into the earth? If you have a strike slip earthquake, you're not sending any energy straight down, so that's not going to help you out. Deeper earthquakes you'll get much clearer signals from, so if your earthquake is deep, you're going to stand a much better chance of seeing a core phase. How big the earthquake needs to be also depends on how noisy your station is at relevant frequencies. So because of the frequencies we're looking at, quite often if you look at data from ocean islands, we have big noise problems, and that's a well-known problem for lots of different frequencies of seismology. If you think about how often your waves hit the beach, you can see that if you're looking at maybe 5 seconds or 8 seconds is the place where we see a lot of that noise from the oceans. So you want a quiet station. The stations in Antarctica, which would be really useful for some of the things I'm going to talk about, have big problems with noise from calving glaciers, say. That's not overly quiet as a process. So the size of earthquake you need will depend on a lot of factors, but on a good day you can get something from a 5. On a very good day you can get something from a 5. On a decent day you can get something from a 5.5. I will say I'm going to show you a little bit of my data later on, and I keep somewhere between 3 and 5% of the seismograms I look at as having a couple of phases I can see. And that will again vary depending on what sort of technique you're doing, what you're looking for, but you look at a lot of data to get anything out because of all those different problems. So I've painted a picture of an inner core, which is this nice ball of mostly iron with an exciting sprinkling of other elements. And at first guess, that should be really homogeneous. It should be kind of plain and boring. It's taken a very long time to grow. It's mostly iron. It's growing out of mostly iron liquid. It should be kind of dull. And yet with the inner core, each time you look, you see more complications and more problems and more exciting details to explain to give us all jobs. So this is a figure from a paper from 1986. And 1986 was a good year for the inner core. This was one of 2 papers which are published back to back in one edition of GRL. And this paper talks about travel time anomalies for waves which go through the core. In particular, it's talking about that PK-IKP, so waves which go right through the inner core, and we're looking here at a picture for nearly vertical rays, so they're traveling nearly through the center of the inner core. And they're just plotting up travel time anomalies. They're plotting helpfully black crosses for things which are negative and pluses for things which are positive travel time anomalies. So I did my best to help you out, and I've colored a bunch of them in. Essentially, and they've plotted this in a slightly unhelpful way, the anomalies are plotted at both the station and where the earthquake was. So you're seeing places where you have an earthquake and a station which are often in the poles with these blue slow anomalies. It's not the easiest figure to work out, but there are definitely patterns in where the travel time anomalies are. What would have really helped you guys is if they'd drawn ray paths on this, but we can only ask for that now more than 20 years later. They expanded the anomalies they saw in terms of spherical harmonics. And they got these weird stripy patterns that may, if you stayed out quite late last night, look like a pair of evil eyes bearing down at you. These stripy patterns we're going to see echoing through the rest of this morning's talk. Essentially, you're seeing different sorts of anomalies at the poles to the anomalies you're seeing close to the equator. And there are 3 panels up here corresponding to 3 different distances. So the biggest epicentral distances will tell you about structure deepest in the inner core. So this is 170 to 180 degrees, which corresponds to a turning radius of 0 to 370 kilometers. So these are going right through the middle, these waves which see this stripy pattern. Waves which travel and turn somewhere between 370 and 880 see a stripy pattern. And the waves which only care about the shallowest bit of the inner core, the top 20 or so kilometers, don't reflect this stripy pattern of travel time anomalies. So the authors of this paper and the paper it was published right next to said, we think we know why we have these stripy patterns. We think that this is the signature of anisotropy in the inner core. We think that different things are happening to rays which travel in different directions through the inner core, and that this is telling us about inner core anisotropy. I'm going to explain the logistics of this a bit more in a minute. But they made an anisotropy model. They subtracted their anisotropy model, and their model completely removed the stripy patterns from the bigger distances and made all the distances look like each other. So they've taken an anisotropy model, they've corrected for it, and they've got rid of that weird evil eye stripy pattern. And the sort of anisotropy they were considering looks like this. We have fast rays traveling north-south through the inner core, and slow rays traveling along Earth's equatorial plane. This is actually a really, really simple symmetry system we're talking about here. We have a fast direction, and we have a slow equatorial plane. So you can travel from Indonesia to Africa, maybe a bit short of a distance, but you can travel anywhere on the equatorial plane, and you'll get the same sort of travel time. The special direction is north to south, and you remember I said I would really like if there were better stations in the Antarctic. You can imagine that if this is completely the fastest direction, the wave path you want to study has some sort of earthquake at the North Pole and a seismometer at the South Pole, or vice versa. So this is the symmetry system we're talking about. It's nowhere near any of the complicated systems like the orthorhombic symmetry. One way you could imagine it was if you had a hexagonal symmetry. So think of your hexagons in planes with a fast direction up the axis and then a slow direction on that equatorial plane. And the mineral physicists are starting to pull faces. And I know that that's not quite how that works, but you can think of it with some sort of columnar symmetry. And that can actually give you interesting slow directions to talk about.
I got a quick question on the last slide. So what's left over looks happily degree 2 and somewhat like what we're used to, but is that fast in the Pacific and under Africa?
Yes. I'm pretty sure that they'd corrected for mantle structure already. I'm not 100%, but I'm pretty sure that they'd already corrected for mantle structure, which I suspect has just led to an overcorrection back the other way.
Okay. It was a
I
little
think what they were really
unexpected when I
excited about was
looking
they'd made all the patterns look the same.
Mm-hmm.
And then you see something which is dominantly that degree 2 structure. And if it's slightly shifted between the different panels, it's a little bit high here, it's a little bit towards Asia here. It's probably where we think of as the degree 2 bullseye. But
it looks like everything's shifted west of what the typical degree 2
so
pattern is.
they've made one simple anisotropy model, and they've said things look better than they did before. You can make all sort of mantle inferences, but using these core phases isn't going to help you for the mantle.
Can you switch back to the previous one just so I can get a sense of the difference in amplitude of the structure? No, before. In absolute time. Yeah, there we go. Okay. So
This one?
No, the one that you were at previously. If you can flash between the corrected and uncorrected.
Okay, so we've got corrected.
Yeah.
Sorry, uncorrected. This is the raw stuff. And then after we fixed it.
Okay, so it's like a factor of 2 difference in signal.
And what you physically see when you look at these is you see travel time anomalies of 5, 6. If you're looking at raw travel times, maybe 9 seconds for these P waves. That's the number for the travel time you're measuring, you're talking about. That's how different it is to your reference model. Okay.
So how do you know the Earth's inner cone is located right at the center of the Earth?
So that's a good question. Why do we think the inner core is in the middle of the Earth? And I'm actually going to talk later about some people who think that maybe it's not stationary in the middle of the Earth. But you can imagine that the inner core is very dense. So to bring it into hydrostatic equilibrium, we would like it to be in the center. I think maybe the question that's more relevant is, how do you know if it's not more of an oblate spheroid? So how do you know if it's not squished like the whole Earth is? And we don't think it is, to the degree that could explain this. It was originally an idea that maybe the inner core was just not very spherical, but that didn't work out. And the inner core really should be in the middle of the Earth because it's heavy and gravity will bring it back there. That's a quick answer. And how squished the inner core can be maybe could tell us something about viscosity in the inner core. And that's something that, as far as I know, we still have 10 to the 6 error bars on inner core viscosity. Some people will argue about that number. And I think maybe Bruce isn't here to tell us his favorite number. But some things we know very poorly about the inner core, and viscosity is definitely one of those.
Jessica? If you go back to the evil eye figure there.
I shouldn't have called it that, should I?
No, it really looks like that to me, so that's fine. So I don't understand one thing here. So you're talking about this anisotropy being north-south, and yeah, I can see it faster north-south, but I also see azimuthal variations in the, along the equator.
And in fact,
Why is that not
those
included?
variations are the things you see in the next picture after you correct for the anisotropy model. So it's not a completely stripy pattern. Remember, this is made of spherical harmonics. You could make a stripy pattern with spherical harmonics. That would be okay. But what we're seeing are a combination of several things. The dominant pattern, though, is the stripiness. And I want you to recognize the stripiness when I show you some normal mode stuff in a bit. So I've made this bold claim that the inner core is anisotropic. And if we want to quantify that, we're going to need some way to quantify ray direction. So we're just going to use zeta. Zeta is the angle between the ray as it goes through the inner core and Earth's rotation axis. So Earth's rotation axis is going to be our fast direction, and then a small zeta will give you something which is relatively polar and fast, and a zeta of 90 will give you something in the equatorial plane. That's the parameter you need. And so people started doing studies. They started using different reference phases. This is a Nature paper from Ken Krieger, who used that PKP BC phase, so the one which gets into the outer core but doesn't get into the inner core, as a reference. And they find curves like this. So we've got a plot of cos squared of the ray angle, so equatorial things down here, polar things up here, and these really strong curves of travel time anomalies. These polar paths have travel time anomalies compared to a reference model of the order of 3 or 4 seconds. But the equatorial paths are pretty well behaved. So that's one study. That was 1992. This is a paper from Vinnick and co-workers. They used a different reference phase. They're seeing exactly the same pattern. They're seeing well-behaved equatorial paths and polar paths, which here have travel time anomalies of 6 or so seconds. They're using the reference phase, which turns more shallowly in the outer core, so they can look at the inner core that's deeper. You need different reference phases for different distances. So we're using different reference phases, and we're seeing this distinct signature of anisotropy. And I really wanted a colour figure next, so here's a colour figure. We can plot with the one reference phase, the one which is relatively close to the inner core phase, or the reference phase which travels more shallowly in the outer core, so it tells you about structure deeper in the inner core. And we can see considerable anisotropy. These are now polar paths down here and equatorial paths up here. And if you fit a best fit line of the right form through these, you'll get of the order of 3 or 4% anisotropy. So there is now good evidence for anisotropy in the inner core.
Hey Jess, I just can't resist asking you, because it's so clear in that figure on the left where you use the, I guess, more appropriate reference space, that there's kind of a weak dependence with your angle, very weak dependence on your angle, and then there's at about 30 you see just 2 populations, a low and a high population. Why would that be?
So the low and high population is what I'm about to get into. The curve that we fit here, this is a curve which is a quartic in cos of the angle. And that's actually what you'd expect for weak anisotropy in a hexagonal system. That's the standard curve we fit, is a quartic in cos of the angle. And it sometimes looks like an L shape to people. It looks less so here. It looks less like an L shape. The reason it looks worse here and better here is because the data coverage is incredibly clumped. Okay, we don't have smooth data coverage. And what you said was it looks kind of like we have 2 populations. And some people in the audience will think that I've somehow paid you to set me up for the next slide, because it does look completely like 2 populations. And in 1997, there was a paper which said that we've been looking at this anisotropy in the inner core. And if we look at how the travel time anomalies are geographically distributed, it looks just like there are 2 populations. So these are travel time anomalies of east-west paths. These are equatorial paths. And we've got positive anomalies in black, negative anomalies in white. And it looks like you've just painted the two halves of the globe different colours. The east of the inner core is different to the west of the inner core. And here I'm saying east and west. I'm going to keep on saying east and west. East we're roughly defining as somewhere on this side of the Greenwich meridian, and west we're roughly defining as somewhere on this side. There are ongoing arguments and discussions and publications about how you'd split these two bodies up, but the two halves of the inner core are different to each other. And these are just the equatorial travel times. So these differences are contained in the relatively small scatter up here. If you flick forwards and look at the polar paths, where Ved said he really saw two different populations, what Tanaka and Hamaguchi showed was that there are really big differences in the polar paths. These polar paths here have really big travel time anomalies. This scale now goes to 5 seconds. And these polar paths over here are tiny travel time anomalies. So the reason you thought you could see two different populations for those polar paths was because there are two different populations for the polar paths. The inner core has a hemispherical nature, and it's really weird. I started doing my PhD, and one of the things I looked at was some of these body waves. And I'd done normal modes for a bit, and body waves were the next way to look at the inner core. And I didn't really believe it. I thought if I picked my seismic data really carefully and covered up stuff like what the ray angle was, maybe it would go away. So I did a whole bunch of work and then a little bit more work after my thesis, and it doesn't go away. It doesn't matter how much you cover up the station information when you pick your seismograms. This hemispherical nature jumps at you out of the data. So here I've split those travel time anomalies into the eastern hemisphere and the western hemisphere. In a really simple way, I've just said, where does this wave get to the deepest bit of the inner core? That's the hemisphere I'm going to assign it to. And using the two different reference models, so there are two different reference phases, so using two different depth ranges, essentially, we're seeing an eastern hemisphere with a small amount of anisotropy, about 1%, and a western hemisphere, that's shown in red, of kind of more than 4% anisotropy. So we're seeing really strong differences between the two hemispheres. And this solved one problem when that 1997 paper came out, because people used to say, maybe we have anisotropy in the inner core and it's just got a tilted axis. What they'd actually been doing was sampling with uneven ray paths that hemispherical pattern, but they'd interpreted that as the axis of anisotropy as being tilted. I'm going to talk to you a bit more about how we could make this seismic anisotropy, but you really want something which is aligned with Earth's rotation axis and where the average magnetic field north and south are. So tilt was a problem. Barbara.
If you go back to the previous figure, I just can't resist making that comment.
Of course.
Most of these data that are very large anomalies in the Western Hemisphere are from a very specific path, which is from the South Sandwich Islands to Alaska, that nobody really has explained yet. And if you remove those paths, actually, you don't have very strong anomalies. And I would say this data set is missing data between zero travel time anomaly and whatever it is, a fractional of 0.02. That fills up if you have a complete data set. So it looks much more like an L curve.
So over here, this data is strongly from one set of ray paths. And these are earthquakes in the South Sandwich Islands, which you can detect in Alaska. And this is by far the strongest signature of anisotropy. So Barbara is completely right. If you take away these ray paths, and that takes away a clump of these ray paths, you're going to lose the signature of the strongest anisotropy. The other thing which we haven't... Okay, you're definitely going to lose the strongest travel time anomaly signal. The other thing which Barbara didn't say is there's actually very little data that's really north-south. Some of the data, which I didn't use, but which people have tried to use previously, was actually from Russian nuclear tests in order to try and get some more of those north-south paths. So we've got significant problems right now from this figure, ascribing this all to anisotropy and a hemispherical pattern.
So what do those data look like from the Russian nuclear test?
Oh, they're really clear, because the nuclear explosions will send
But do they show
P-wave
extremely
data right
large?
for you. You can see anisotropy with some of those data, and people have used those data to look at other things as well. So
the question is how strong, right?
So those paths...
When you make models of the Western Hemisphere, you know, some of
so
them
those
are
paths, when you make
outrageously
models-
large, and they all depend on these anomalous paths. So I think that
so
point needs to
the
be
paths that Ved asked about are not the same as the paths which show the anomalously strong signal. They tend, because of where they come from in Russia, they tend to go through the inner core somewhere close to the boundary between east and west. So they don't show travel time anomalies which are as strong. They show, I couldn't put a number on it, but of the order of maybe 2%, maybe 1.5% anisotropy from those particular paths. And the point I'm trying to make here is the strongest anomalies we ascribe to where the anisotropy is strongest, and that's what Barbara is saying I haven't yet proved. But it's all right, Barbara, I'm going to do it in the next 15 minutes.
And those paths from South Sandwich to the Aleutians, the difference in travel time can't be due to propagation through the slab and then back up a second slab?
So that's one of the
Can't be in the
concerns, that many of the best earthquakes for doing this, and the earthquakes in that South Sandwich region, are subduction events. So one of the concerns would be maybe you're getting weird focusing where you're skimming along one slab and then doing exactly the same thing back up on the other side. And furthermore, that your reference phase isn't doing that, because your reference phase has a very similar takeoff angle. But your reference phase wouldn't be doing that in that case. So that's one reason that people are concerned about some of these body wave travel times, and they're good concerns to have. Because if the strongest signature is coming from one geographical location, can we really call that a global hemispherical pattern? It was there in the equatorial data. It's a smaller signal because the equatorial data don't see very much anisotropy. So what we might want to do is to use normal mode data, because normal modes see big structures in the Earth. So this is that picture we had from the body wave paper, the evil eye picture. I'm going to keep on calling it that now. And this is the splitting function. The reference is down here. This is the splitting function of a mode which cares about the inner core. And modes which are sensitive to the inner core really strongly see the anisotropy in the inner core. So this is a splitting function just of the type I introduced you to last week. And what I said last week and what I'll say again today is the splitting function basically tells you about how a mode sees Earth structure under each point in the Earth. So what we see here is the pattern you get familiar with if you look at inner core anisotropy, because you've got stripes at the North Pole and the South Pole and a different colour in the middle. And clearly you also have more details. But the dominant pattern is a stripy one. And that's true for all of the modes which care about inner core anisotropy. You get this stripy pattern when you look at that mode splitting function. So these are splitting functions measured by Arwin-Joyce. These are two modes which are sensitive to the inner core. You can see, looking at their sensitivity kernels, that they're sensitive to the whole Earth. It's not just that they care about the inner core. But they have this really stripy pattern. They also have what many people who think about the mantle will recognize as degree 2 stuff going on near the equator, because they see the whole Earth. They care about the mantle as well as caring about the inner core. But you can use normal modes to look at anisotropy in the inner core, and you can use normal mode data to quantify anisotropy in the inner core and make models which don't require any use of body wave data.
Quick question. The kernel in the A shows no sensitivity in the inner core.
Oh, that's sensitivity in the inner core.
Okay.
It looks titchy. You look at that and you think it doesn't care at all about the inner core. But if you measure the splitting function and predict the splitting function using a sensible anisotropy model, you would predict something that looked like this. If you predict what that splitting function would look like just using a mantle and crust model, you'd get that. That tiny sensitivity to structure in the inner core is what makes this stripy pattern. And that's really dramatic, because the sensitivity looks minuscule. Ved couldn't see it from back there. But that mode really cares about the inner core, as do many of these modes.
So again, Jessica, just from this slide, you can't say that it's in the inner core. You can say it's not in the mantle, but you can't really say that it's in the inner core.
Yes. So right now, the picture you can see on the screen is mantle plus one particular crust model looks like this. Normal mode observations look like this. So can we require that structure to be in the inner core? For the moment, I'm going to say the outer core is boring, and then I'm going to come back to the outer core at the end and show you some reasons why we think that's a legitimate thing to say. So people have made a variety of different models for inner core anisotropy, and the cool thing about using the normal modes to look at inner core anisotropy is you can also extract information about shear wave anisotropy. I've only been showing you P waves. It's incredibly difficult to see a wave which is a shear wave in the inner core. But normal mode models can teach you about that. These are 4 different normal mode models. They've all been made in really quite different ways. This is a model which Barbara and one of her either students or postdocs worked on. They did a few different things. So they used body wave data as well as normal mode data. And they also didn't use splitting functions as an in-between step. They went straight from spectra to the model. This is one of the earliest models where they said, let's make everything really simple and boring. Let's make anisotropy constant through the inner core. And the way we parameterize these things, we have 3 parameters. One tells you basically about P wave anisotropy. One tells you more about shear wave anisotropy. And the other one tells you more about intermediate angles. But you can make all the parameters up using the love equations, the love letters that Barbara defined in her talk. So we've got different models.
The mode sensitivities, looking at those figures versus depth, where by eye should we not believe it? At what depth where there's no sensitivity? Because you have the plots go for 1200 to 0.
So normal modes, their sensitivity mathematically goes to 0 at the middle of the inner core. Okay? And their eigenfunctions go to 0 at the middle of the inner core, all apart from those weird Schlichter modes. So the question Vern's asking is, do we trust structure at 200 kilometers? Well, this model had body wave data in it, so that gives you some sensitivity to deeper structures. This model is all straight lines, so you can do what you want, but it's straight line anyway. This model used the sensitivity kernels, and because there was no sensitivity at depth, the model goes away at depth. And this final model here actually did a Monte Carlo search with a neighborhood algorithm. So even though you could be in the null space, it's ended up with structure at the bottom, although the structure, depending on who you talk to, could be slightly singular at the center in this model. But if there's no sensitivity, that's no problem.
What was alpha, beta, and gamma again?
They're combinations of the love letters.
But so if I look at these, I see that there looks like there's a degree of similarity with gamma, and the rest seem very, very different when I'm looking at this.
So alpha, my recollection is that alpha is P waves, beta is S, and gamma is in between, but I wouldn't quote me on that. I could have some of those backwards. Yeah, one is C minus A, one is L minus N. They're combinations of those love numbers, and I wouldn't like to try and quote them off the top of my head right now. So we have models that look vastly different to each other, all made from normal mode data, and many of them made from similar bits of normal mode data. But it turns out that even though we have models which look different, we have bigger problems, because if you let modes couple in the inner core, and I talked about mode coupling, you can do all sorts of crazy things to these modes. So when you let the modes couple, this is for that 13S2 mode, sometimes you'll see dramatic changes in the frequency of the mode. Sometimes you'll see dramatic changes in how much the mode attenuates. And that's actually worse if this is for putting hemispheres in the inner core. So let's flick back to an observation of a splitting function. This is a splitting function observed for an inner core sensitive mode. It's got our stripy pattern. If you predict the splitting function for this mode just with mantle structure, you get something which looks a little bit like where there's subduction in the mantle. So if you predict just using a mantle model, you'll get something like this. If you predict the structure using, I'm pretty sure this is Barbara's model of inner core anisotropy, you get something which looks a lot like the observation. So our predictions using the existing models match our observations well. But I said that the coupling was important for the modes in the inner core. And so what you can actually measure is a cross-coupled splitting function. So you can measure how 2 modes interact with each other due to the structure in the inner core. And that can tell you about odd degree structure. And I said in my normal modes lecture, and somebody asked again in the questions and emphasized this point, that an individual normal mode can only tell you about even degree structure in the Earth. If you want to look at odd degree structure, you have to look at cross-coupled splitting functions. So here's a cross-coupled splitting function. This is a cross-coupled splitting function for a pair of normal modes. This is 16S5 and 17S4. And 17S4 only shakes the inner core, basically. It's not sensitive to the rest of the Earth. Sensitivity is confined to the inner core. So it only cares about structure in the inner core. And when you look at the cross-coupled splitting function, you see the same hemispherical pattern pop out. You see the signature of the east is opposite to the signature of the west. So we have this hemispherical pattern popping out of the normal mode splitting functions. Normal modes tell you about a global gross average structure. The pattern in the observation is hemispherical. The east has the opposite signature to the west. We know that one of these two modes is confined to the inner core, doesn't really care about anything in the rest of the Earth. But if you were to predict this splitting function using structure in the mantle, you would see nothing. And that's because I said one of the modes doesn't care about the structure in the rest of the Earth, so they can't couple in the mantle. That's why you get nothing. If you take an existing inner core anisotropy model and chop it in half, which, by the way, it was completely not designed for, then you get the same sort of pattern as you do in the observation. I've taken a model which is meant to represent global, well, Owen took a model which is meant to represent global structure and chopped it in half, so it's designed to represent a global average. We bump up the amplitude so the global average is the same. We get this hemispherical pattern because it's in half of the inner core and not in the other half of the inner core. And this normal mode observation matches those predictions. So the normal mode splitting functions are telling you that you have this hemispherical structure in the inner core. I'm not quantifying here whether that's anisotropy or whether that's isotropic differences, but the hemispherical pattern is there in the normal mode data as well as in the body wave data. So we don't have to worry about it just being the South Sandwich Islands polluting our data set. And that was a real concern before. It could have just been that one dominant ray path weirdness. But we now have big data to tell us about the global structure and smaller scale data to tell us about the details, and things are less bad than they were 25 minutes ago. Zach,
well,
the question, then
okay.
Barbara.
So I will not contest the hemispherical differences. I will contest the strength of the differences.
No, and I think that's completely accurate. And maybe what has happened is we were really lucky with where the South Sandwich Island earthquakes are. Maybe we've just managed to see the strongest stuff. Maybe what we're seeing isn't really as strong and there is some path weirdness, but there is definitely a hemispherical pattern in the normal mode data, which seems to mirror what we understand from the body wave data. And by the way, these black lines you're seeing on here are the lines drawn from that body wave data set that I showed you before. So that's where I put the hemisphere, that's where the hemisphere boundaries are on those pictures. They're dividing up where the body wave data goes.
So while we're talking about those lines, why is the west hemisphere smaller than the east? Right, I know this is something
because that's where I thought the boundaries were. That's where I still think the boundaries are. So the hemispherical pattern isn't 100% degree one. They're not 180 degrees of one hemisphere and 180 degrees of the other. And there are many publications about exactly where those boundaries are. And I don't think as a community we've pinned them down. I can tell you my favourite numbers. If you ask Lauren, she'll tell you her favourite numbers, and they'll be a bit different to mine, but not tremendously different. If you ask Vern, he'll tell you slightly different numbers for where he thinks the boundaries might be. And the nature of those boundaries, whether you jump dramatically from one hemisphere to the other, is also something where different people have different views. And I'm going to show you some data from that as well.
Just on the theme of where the observations are, I mean, is there a reason to think that it's just linked to where we have continents? That's where we're more likely to be picking up this
the
dividing
normal
line?
mode data is seeing a global average. That's the whole Earth shaking. So you're not biased in the same way with the normal mode observations. We do dominantly have stations on the Earth, but you're looking at the different modes of whole Earth shaking. So the normal mode data, you don't have that geographic problem. That's one of the strengths of the normal modes. The weakness of the normal modes is they can't tell you about small things, they can only tell you about big things. But the strength is we don't have this problem of poor station coverage in the southern hemisphere and in the oceans. So I'm going to skip through a few things and briefly talk about why we might have anisotropy in the inner core. This is a cartoon of how I think the inner core could look. I don't know what's going on in the middle. It's hard to see with normal modes. It's possible to look with body waves, but it's not easy. There is an isotropic layer, which I haven't really talked about, at the top of the Western Hemisphere, and then there's relatively strong anisotropy in the Western Hemisphere. The anisotropy is much weaker in the Eastern Hemisphere. And the next question is always, why is it anisotropic at all? I mean, never mind this hemispherical weirdness. Why is there anisotropy? And it's the inner core, so the answer right now is we're not quite sure. Essentially, you can think of making the anisotropy using two different sorts of forces to align crystals. If you want to line your crystals up, you can think about thermal gradients, or you can think about magnetic forces. The other thing you can do is you can have some sort of shape-preferred orientation. This was the other sort of anisotropy that's mentioned. And then you'd need to line up shapes. So whether you're lining up big dendrites or maybe liquid inclusions, you could line up shapes. But the big forces you'd normally talk about are thermal gradients and magnetic forces. You need the mic.
Is there any way to seismically tell the difference between shape-preferred versus lattice-preferred orientation? No,
especially not in the inner core. So this is one of my favorite models. This is a thermal way to do it. We heard yesterday, and we've heard before these last fortnight, about how heat flow works in the outer core. And you're actually extracting more heat in the equatorial plane of the inner core. So more heat is being pumped out there. So this model, this is an idea from Yoshida and co-workers, is that the inner core actually grows as an oblate spheroid because of more heat being extracted at the equator. But that's not hydrostatically stable, so it then deforms back to being spherical, and that deformation is what lines crystals up to give you observable anisotropy. This is one of many ideas. I quite like this one because it doesn't feel as weird as some of the other ideas. We have good physical reason to think that the heat flow is like this, but this is only going to work for certain viscosities of the inner core. The inner core has to be runny enough that you can deform it, but not so runny that the deformation happens before individual crystals have worked out what's going on. So this could place bounds on viscosity in the inner core, which we don't have at the moment, but only if this was true, which we don't know at the moment. There are a few different ways you could use Maxwell stresses and Lorentz forces to align crystals. And it's thought that, this is a paper published by Carato, that you could actually, if you 100% knew the anisotropy in the inner core, you could make inferences about the core's magnetic field, which would be nice, but there is no way we 100% know even the phase we have in the inner core. We don't know if it's BCC or HCP ion. So this one at the moment is still a long shot. And you can get different sorts of anisotropy and alignment with different arrangements of magnetic field. And in particular, that's the difference between the strength of the toroidal component and the poloidal component. And finally, you can do this, I don't know how that looks on the screen, but you can do this shape-preferred orientation thing. So one of what I think is one of the slightly more original ideas, because I'm being recorded, is that you have ellipses of melt completely through the inner core, and those ellipses are all lined up to give you observable seismic anisotropy. Okay, well, it definitely could be something you could line up if you could have melt right through to the center of the inner core. But basically, there are as many mechanisms for making anisotropy in the inner core as there are people who've proposed them. In fact, two of the different magnetic force mechanisms were proposed by the same author. So we probably have more mechanisms than we do authors. So anisotropy is there. The strength is something which Barbara and I will continue to debate for a very long time. We have good evidence from normal mode data, and we have some confidence that the body wave data isn't therefore just spurious. And we're just over halfway through, so I wanted to briefly detour and take your minds off the inner core for a moment to the oceans, because this is something that Barbara mentioned in her talk that I'd mentioned over coffee, the prospect of putting seismometers into the sea. So as a brief detour to the oceans, this could fix our coverage problems for looking at the core. It could fix a bunch of seismological problems, and these are projects. One is primarily being done by my colleague at Princeton, Frederick Simons. That's this project over here. It's called Son of Mermaid. It's called Son of Mermaid because this is data for a mermaid project by Husnelay at Nice. And they have seismometers which float in the water column and can detect earthquakes from the other side of the Earth. They can detect the P waves. You've got the P wave which goes through the whole Earth. It goes up into the water, and it's then detected by a floating seismometer. And this, it's a crazy idea. This is data from May this year of a magnitude 6.5 earthquake detected by a floating seismometer somewhere out in the Pacific. And you can see arrivals in this data. You can see the P wave from this earthquake come in. So when Barbara said maybe floating seismometers, this is data that's being gathered by a test run. This deployment from the NICE group is actually to try and look at structure of the Galapagos plume. So currently their floating seismometers are out in the Pacific. The Son of Mermaid project tries to get around some battery limitations from the Mermaid project. And the Son of Mermaid project, I think they're currently out in the Bahamas doing a test deployment. They did a test deployment before, and then after about 24 hours, it got run over by Hurricane Sandy. The cool thing about this is going to try and harness wave energy to power the floating seismometer in the water. So the waves are powering it. It's being taken around the Earth by the ocean currents, and it's going to send you back seismic data. So this is a brief interlude away from the core to tell you that maybe things are going to get better. Before you ask your question, neither of these are my projects. I only know the people who do them.
I just wanted to add in that there's another related ocean bottom one.
Yes.
Do you have the wave glider one, the one out of Scripps?
So I don't have any figures for that, and I know less about that.
I just know because John Berger's on the GSN standing committee, and he talks about it all the time.
Yeah, so there are a few different groups doing these amazing, crazy things. There are also other ideas about how you can have different things on the ocean floor. Yeah. OBSs at the moment, you have to deploy them, you have to come back and pick them up. These guys from this project, you tell them you're coming to get them, and they should come back to the surface in a few hours when your fishing boat goes past. So this is a very different proposition to doing a whole ocean bottom seismometer deployment.
I'd just like to say that the Scripps one, the nice thing about that one is it's real OBS that's on the bottom, and you know exactly where it is, and there's just a wave glider going around that does the telemetry.
So I think that might be called the ASOS or
yeah,
ASOS,
he's got. I don't
that.
ever remember acronyms, so.
So if you're interested in this, there are other cool projects like apparently the
yeah.
Scripps one.
And that's also not mine, obviously, since I don't know the acronym.
Okay, so I'm going to have a brief detour into inner core rotation, which is really controversial. So it's a good thing to talk about on a Saturday morning. This is that figure that I showed you right at the beginning of the magnetic field. And this magnetic field simulation had a really weird outcome. It said that one of the things that could happen here is that the inner core could be rotating relative to the mantle. So the whole Earth is spinning round. We have days and stuff. But the inner core could be spinning at an ever so slightly different speed to the mantle. The planet isn't moving all at the same rate, but the inner core is going a little bit faster, or maybe a little bit slower. And this was an outcome of this magnetic field model. This is a quote from Paul Richards, who said that the model rate of about 5 degrees a year seemed fast enough to warrant a search for seismological indications. If the inner core isn't homogeneous, which I hope you think isn't, I've convinced you at this point that it's not completely homogeneous, and it's moving, then can we seismically detect that? And the trick you use, or at least you would use if the screen was better quality, is that you can use some of the South Sandwich Islands earthquakes, and you can look at earthquakes called doublets. So you've got earthquakes which are happening in the same place with the same mechanisms some time later. That's what we'd call the seismic doublet. And so overlapping here are two outer core phases, which are the same shape from this earthquake in the same place recorded sometime later. Two AB phases, which, if you can see from the back, are the same shape recorded from these two different earthquakes. And two inner core phases, which are different to each other. So we've got one peak here on the faint grey one and one peak here on the black one. So the inner core signature is different, even though the outer core signature is the same. And this is the evidence that Song and Richards used to say, we can see changes in the inner core. Maybe the inner core is rotating faster. And this is an amazing idea. And there are a few different ways you can think about this, how you could seismically think about looking for this. So the Song and Richards idea actually required that the axis of anisotropy was tilted. So after some time, the inner core has moved around a bit. You're looking at a different angle with respect to that anisotropy axis, so you're seeing a different amount of anisotropy. We now think that the tilted axis probably was just due to uneven sampling of the hemispherical structure. But that was their original idea. We can now think of a bunch of different things to cause observable variation. So if the inner core is going round and you've got some topography, then if you look at reflections from the inner core boundary after some time, you'll see a different bit of topography, you can see a different signal. You can look at waves which go through and hope to sample some heterogeneity which then moves as the inner core rotates. Or you could try and look for scattering. And that turns into this whole industry of people hunting for inner core rotation, using different techniques with different ideas. You have to make assumptions about some of the different properties. And people do see temporal variations. I showed you that pair of seismograms. It's not the only one, where for very similar earthquakes, the outer core arrivals look identical, and the inner core arrival looks different. I think there are problems with big inner core rotation. So this is going to be me giving you a personal viewpoint on this. One of the reasons I'm not a fan of this big scale inner core rotation, and some of the quotes were at 1 degree a year of rotation relative to the mantle, are from the normal mode evidence. This was a really cool idea. It was Gabby Lasky and Guy Masters who published this, and they measured splitting functions using normal mode data for old data and for new data. And then they said, what do we have to do? How much rotation do we have to get my old splitting function to look the same as my new splitting function? So they're looking at big scale structure, rotating the inner core. And the cool thing about this is you can do it for a bunch of different normal modes. The inner core is rotating, then all the normal modes should see the same rotation rate. So this is a way to get independent measures using the same technique of what should be exactly the same rate over exactly the same time interval. Except that the normal mode data, some of the modes think the inner core is going in one direction, some of the modes think the inner core is going in the other direction, and the only way to get the error bars to meet up is if there is no net rotation. Okay, so the normal mode data, their mean rotation rate is 0.01 degree per year.
Jess, has this been done more recently with like the last sort of 15 years of data?
John Woodhouse had a PhD student who looked at it and found no net rotation. I'm not aware of anybody having done it since then.
In terms of, yeah.
I mean, it's primed to be updated, and certainly people who make measurements of normal modes have done. There is so much more normal mode data out there than there used to be. So I don't think so. I think these are still the most recent rotation rates from the normal modes.
There's a guy who's working at Lamont from Peking University who's using ambient noise from near antipodal stations to image PKIKP and is looking for inner core rotation right now.
Well, there we go. There's a whole new technique. Ambient noise tomography of the inner core.
From body waves, there are other studies. We had a study looking at inner core topography.
Yeah, and there are a selection of other studies. And this is the data by publication year. So this is rotation rate. This is when people published their paper. This is me drawing a really crude line through it. What I will say is that there is definitely some sort of temporal change. We saw those seismograms. Either it's a problem with the earthquake not being a true doublet, or there is something changing. The gross rotation rate, I don't think, is 1 degree a year. I don't think anybody thinks it's 1 degree a year anymore. There is some sort of temporal change. Some people are now arguing for the inner core to be wobbling backwards and forwards. There's one person who's actually correlated that argument with geomagnetic jerks. In fact, there might be 2 different papers now saying maybe it switches rotation rate when there's a geomagnetic jerk. There are lots of different ideas out there, and it's certainly one of the places in deep earth seismology where I've seen the most papers and counter-papers and comments on letters and comments on comments on letters.
So one of the issues with the body wave data is that you need a long time series, like 30 years or 40 years. And I think this is going to be maybe results, soon. But the early papers, the Song and Richards, they had to reach out to data from the 60s, where the instruments were different.
Yeah.
Even if they had a doublet, they had different instruments.
Completely.
And so there
and
were
they
all
also
sorts
had
of
to
issues.
digitize analog data. They went back to paper seismograms to do those early studies. And the work that they put into this was fantastic. And I don't think we have an answer yet, and I think Barbara's completely right that we will get an answer just with a longer time span of data. And that may well be one of the reasons that we're seeing smaller numbers being suggested now.
Hey, Jess. So if you go back to to Guy's figure, yeah, that one. So figures like this kind of perturb me a bit, and maybe it's because I've never worked with splitting functions, but presumably between 1981 and 1996, the data coverage has changed quite a bit. And when one constructs splitting functions, like you're showing, one solves some kind of an inverse problem to estimate it from given a particular set of paths on which these frequencies have been measured. And so, to me, the differences between these splitting functions without any mention of uncertainty of either one, and particularly the 1981 one, are truly terrifying.
Yeah.
So, can you comment
I
on...
think so. The first thing I'd say is just in terms of what Gabby did. You'll notice that this is a much smaller time window for this splitting function observation than this one. So this is data from an 8-year window. It's plus or minus 4 years. This is data from a 2-year window. So a lot of the stations we use for normal modes were running by this time. They weren't all. But it is a problem that we now have much better data. And this goes exactly back to what Barbara was saying, that not only did they have shorter time spans to look for the rotation, but we now have so much more data than used to be available.
Just a couple of historical notes. The Song and Richards big number came down from a degree to like tenths of a degree from work by Krieger, who noted that you have to correct for strong lateral variations at the top of the inner core, and that brought the number right down. I think even Song and Richards go down to a tenth of a degree or two recently. I also think the mode group at Scripps has more recent stuff, but I don't know the exact reference.
Well, that would be really interesting to see. And many of these are people reanalyzing their own data and coming up with new numbers. So this is a really cool idea, this inner core rotation. And I think I tried to give you something a little bit more controversial. Something which I'm only very briefly going to touch on in the interests of time was some work published by Lauren, who's sitting at the back here, who actually looked at different depth layers in the inner core and looked at where the hemisphere boundaries appeared to be for different depth layers, and came up with a number that the inner core is rotating at 0.1 degree per million years, which is much smaller. And so this is a completely different pattern. She's using different phases, a different reference phase to the one I've used, but looking at depth-dependent structure and invoking the idea that that tells us about where the inner core was back in time. So we're now thinking about the temporal evolution of the inner core. I'm going to skip over PKJKP, except to say that shear waves in the inner core are really hard to see. Some people have tried to do it. They used to produce tremendously blurry figures, saying maybe they've seen a shear wave in the inner core. There are a few groups now that have observed what are thought to be shear waves. This is one observation. This is another observation of shear waves in the inner core from Barbara's group. PKJKP has a lot of promise to tell us a lot about shear in the inner core. At the moment, it's very hard to observe, and a lot of our information about shear wave velocity in the inner core still comes from normal modes. So in my last few minutes, I will do what I promised. I will skip over inner core translation and talk briefly about the outer core. Give me a minute. More questions than I expected. So I've been telling you about structure in the inner core, which essentially means that the outer core is like the panes of glass in this window. We're looking through something which I have said, or I have inferred, I have promised you, is boring and transparent. And so when we look through the inner core, which by the way is round, not square, we're looking through something which transmits all the information, we're just looking through glass. Is that okay? This is actually one of Barbara's questions, I think. She said, you're saying that structure's not in the mantle, and I said, yes, I think it's in the inner core. Is that all right? The inner core is incredibly transparent. One of the things you can do with the inner core is you can look for these amazing waves that loop all the way around the Earth. This is a pair of ray paths. This is P4kp and P7kp. That means it's a P wave which either has 4 legs in the outer core or 7 legs in the outer core. The attenuation in the outer core for these P waves is sufficiently low that these ricochets, it's really what they are, around the outer core, can be observed. This is a paper from 1974. This is P7kp appearing on a seismogram. So the outer core does have really interesting properties. I mean, the fact that you can have something like P7kp is, to me, really amazing. And this is a picture from a poster that's about to be shown at CIDER, showing that we can see a clear P4kp using a variety of different stacking techniques. And we can actually try and infer things about the properties of the outer core using some of these crazy Etch-a-Sketch phases that loop round and round and round the outer core. So when inner core anisotropy was first suggested, one of the concerns was maybe we're seeing structure in the outer core. And the physical way you could do this, because we think that the outer core is very well mixed, is to actually have different structure in the talar cylinder of the outer core. So talar cylinder is something that we've heard defined already. It's the cylinder you can think of enclosing the inner core. And it's one place where maybe it might not be so terrible if you had some differences. So stuff in between the talar cylinder and outside of the talar cylinder. And so there have been a variety of different studies looking for structure inside the tangent cylinder. This is a study by Anisotropy. The details of this aren't tremendously important. She's using these SK multiples, so things which go into the core as S waves, they bounce as P waves once, twice, maybe more times, and then come back outside. But they're very sensitive to structure at the top of the outer core. So she used these waves to try and hunt for differences between those waves which are in the tangent cylinder and waves which went into the core at different latitudes, and she found no trend. So stuff that's in the inner core in the tangent cylinder, in the outer core in the tangent cylinder, didn't seem to be different to stuff outside of it. There have also been some... No, slide has vanished. There have also been other studies where people looked at the outer core using normal modes. So in particular, there was a study by Ishii and Jaworski who tried to look using normal mode data for structure in the tangent cylinder, and that also found no structure in the tangent cylinder. Other places where the outer core is kind of interesting include this suggestion of an F layer. So this layer would actually be at the bottom of the outer core, and that's where we see Prem and AK135 diverging. And this is something that Vern's worked on extensively. And the idea is at the bottom of the outer core, maybe you have more interesting things going on. Maybe there's a region with slightly different properties. Maybe it's something to do with how the inner core is crystallizing. Maybe it's to do with how light elements are released. But there are suggestions that the bottom of the outer core maybe doesn't look like the bulk of the outer core. And that's something which I think a number of CIDER groups have investigated. And there have been these really interesting papers. This is something from one of Vern's papers that actually tells us that what's going on in the outer core could really tell us about viscosity as well, which is pretty cool. And finally, the very top of the outer core. So the very top of the outer core we heard quite a lot about yesterday. So this is an excellent introductory slide that I managed to steal from Bruce's. If you have all of these different balances of light element release, latent heat release, and maybe cold downwellings, one of the things that's being suggested is we could have a stratified layer at the top of the outer core. We'd like to try and see a seismic signal for that stratified layer. And I think you'll remember a couple of weeks ago, Sana and I stood up here and said, we did this awesome CIDER project. We tried to look for a stratified layer. It's still ongoing because we're not quite sure what we found yet. But the reason that a stratified layer is interesting is because it could tell us a lot about these physical problems. the Mach waves that Bruce talked about would actually be confined to that stratified layer. So we could have interesting physical waves that can affect magnetic field observations caused by this stratified layer. And so there have been a bunch of different people who've tried to hunt for this. This is the core mantle boundary. This is the bulk of the inner core. And people have made all of these different models, trying to look for tiny differences in velocity, which would correspond to tiny differences in density. And at the moment, my personal view is that the jury is still out on these aspects. There are small differences from Prem. Everybody has their own favorite model. If there are any changes at the top of the outer core, they're relatively small, but people are actively hunting for those at the moment. So I think what I'm going to do is try and finish like 5 whole minutes early and see if there are any more questions at this point.
So I know that they've the top of the outer core, they've used things like P7, KP, and things like that. Is it possible for there to exist surface waves at the bottom of the mantle, like Lever-Rayleigh waves?
Yeah, so you can get waves which could be confined to the core mantle boundary. In normal mode terms, these are called Stoney modes. And just as you can think of as the surface waves being being the same as fundamental normal modes, you can actually think about how you could sum the Stoney modes to give you travelling waves through a whisper gallery. And that would depend on the exact velocity profile there. Of course, the problem with those waves is that they're confined to the core mantle boundary, which means we can't see them because they're confined to the core mantle boundary. I think one of the ways we might be able to unveil those is by looking at the coupled normal modes. And there have been some observations of coupled splitting functions. Because the bottom of the mantle is so heterogeneous, those coupled splitting functions of those Stoney modes are really telling you about things like D double prime structure. They're telling you, I think, there's a lot more information and heterogeneity at the very bottom of the mantle than there is at the very top of the outer core. So I think that those modes, although they're sensitive there, are going to be overwhelmed by what's going on at the bottom of the mantle. But that is an interesting way to think about these problems. Mike?
But you said those could potentially tell us more information about the core mantle boundary,
yes,
right? At
completely.
the core mantle boundary.
Yeah, so the Stoney modes really care about what's going on at that solid-liquid interface.
So I'm trying to get a physical image of why there would be anisotropy in different hemispheres. So I understand maybe in the whole core, but I have no physical understanding of how that could be.
Yeah, it's completely ridiculous, right? So if you think about the two different mechanisms, the two different forces that I put forwards, they were thermal gradients, or thermal asymmetries, or magnetic unevennesses. So if you want hemispherical structure, you need to have some sort of variation in either of those forcing mechanisms which could do this. So I flashed really quickly through one figure of the magnetic field. Let me try and find that for you. So this was one idea, which makes people who do paleomag somewhat unhappy. If you take the magnetic field, this is the dipole and non-dipole field, and you remove the dipole field, you end up with this pattern. That's with the same hemisphere lines drawn on. So one thing that we talked about was, and tentatively suggested, was there is an asymmetry in the strength of these fields in the two different hemispheres. Is that enough? I have no idea, and I was one of the authors on this paper. This is a 5 million year field picture, so it's the field averaged over 5 million years. Depending on what you want the growth rate of the inner core to be, and completely depending on what you want the age of the inner core to be, if you want hemispherical structures pervading for hundreds and hundreds of kilometers, we're talking about something which has been constant for hundreds of millions of years. So whatever we do, we're going to have to make it big, and we're going to have to make it stay there a long time. The slides which everybody saw me zoom through were about inner core translation. Let me find those. So this is an awesome cartoon I stole from some CIDER people. Inner core translation says that the inner core is moving as a solid body through the outer core, like that cannonball on that skateboard. And it was actually suggested to try and explain some properties of the very top of the inner core being different on the east and the west. So this idea says that if the whole inner core is slowly translating, or rapidly to some extent, because this would renew the inner core multiple times, the speed is much faster than the speed of inner core growth, then you'd have crystals on one side which are melting, crystals on the other side which are freezing, and then the individual crystals will move through the Earth as the inner core translates, which will lead you to crystals on one side being really old and crystals on the other side being really young. So that could try and explain isotropic velocity differences and attenuation differences, which would be due to grain size differences, but that can't fix anisotropy.
Why would it be moving?
Sorry?
Why would it be moving?
Because it's on a skateboard. So the numerical modelers who've done this say if there's a small perturbation in inner core position, that you will set up an asymmetry, and the fastest way to bring yourself back to hydrostatic equilibrium is to freeze one side and grow on the other side, because you've essentially shifted it off where the melting line should be. That's what you've done by slightly perturbing it. So you'd end up keep freezing on one side and then keep melting on the other side in order to try and stay in balance. So the people who wrote these papers suggested that the numerical modeling said it was a stable mode, that it could keep on sliding sideways. Because it can't explain the differences in anisotropy, it can explain some stuff, but it can't explain anisotropy yet. So I don't see this as having fixed all of our problems. But it's an interesting idea and makes for a cool cartoon. Any more questions?
Could you say any more about the seismic evidence for this outer core stratification, so at the top? Because I remember George Helfrich being very convinced that he has evidence for this stratified layer.
Let me see if I can find one of George's pictures here. Okay, so this is a figure from one of George's papers. And he's looking for a stratified layer at the top of the inner core, again using these SKS multiples. So it's S and then a bunch of little P waves bouncing multiple times off the underside of the CMB. And what you're seeing in these two panels here are real waveforms in this panel from earthquakes in Tonga or earthquakes in Argentina recorded in Europe and Japan respectively. And what he wants you to look at are these multiples which are delayed. So this is the real data, this is the synthetic data, and this S4KS, so it's got these four legs at the top of the outer core, is late here relative to the 1D model that existed. So he's using this sort of data to say that the top of the outer core is slightly slower than the existing models. So we're comparing what's in this ellipse to the stuff that's not an ellipse. And the same is true for these S5KSs here. They also come in late. They should be coming in on the line. They're coming in after the line. So this is the sort of evidence that people use to say that there is a slow layer at the top, and that would correspond to the stratified layer. So that's the sort of data that people use. Fair.
Okay, so not being a body wave seismologist, so that looks quite clear. So what's the controversy?
So it's clear that for this ray path, this set, this is slower than the model. This is only from 2 earthquake locations recorded at 2 dense seismic arrays. So you have to be concerned to some extent about things like the mantle that they've gone through. You're using relative measurements, the same as for the inner core, so you get rid of some of those problems. You also sometimes have to wonder if some of the waves could tunnel a bit into the lowermost mantle. But this looks pretty clear, and I mean, this was a Nature paper saying this.
So it's wrong.
So there is distinct evidence. There's another really nice study.
I think there's some problems with the sense of his velocity anomaly as well, at least in terms of the people that wanted the stratified layer, like Buffett and Siegel. They wanted a high velocity little region,
Yeah.
but his was low.
So that means...
Other model, right? I mean, the observations should be
Yeah, so it's... I think
ones
what we're
that
saying
need
is
to
it's
be explained.
controversial. So if you're changing velocities and you want also changes in density, you also have to care about things like the bulk modulus changes, how are those changing with the introduction of the light elements. So there's the mineral physics of having a stratified layer which is rich in light elements, as well as just saying, hey, I see a different velocity. This is a really nice paper by Alexandrakis and Eaton, and they show, they did a whole suite of different sorts of tests. Prem is up here, their favourite model is here, and then there's this little patch of admissible models with different sorts of probabilities. So there are people actively working on this. They don't all agree, and some of it does depend on the details of the mineral physics. But there's definitely cool stuff out there.